Okay, so welcome everyone and thank you for coming. So today we are going to talk about Log4jshell and then preparing CVEs or the next CVEs with eBPF. So my name is Natalia Ivanko. I'm a security product lead at Ivanko, and then John today couldn't make it, but let's give him some credit. He's a Tetragon lead, a Cilium maintainer, a long-time kernel engineer, and then a staff engineer at Ivanko. So a little bit about motivation and then the agenda today. So first we will talk about what is Log4jshell, why is it so powerful, and then how eBPF comes into the picture, what is eBPF, why eBPF, and then we will take a look into one project which provide eBPF based runtime security. This is going to be Tetragon. And then we will see a demo, how Log4jshell would have been cut with Tetragon. And then we will see some further detection and then prevention techniques. So first, Log4jshell one-on-one, it's going to be a nutshell, not really a deep dive. So what is Log4jshell? So it's basically a vulnerability. It's a vulnerability in a logging library, a Java-based logging library, which allows remote code execution. So it basically allows an attacker who actually controls the log messages to execute arbitrary code on a server. So how does it work and what Log4jshell features allows to do that? So first of all, the Log4j library allows to log messages like text messages from sources that you don't control. So for example, if you have an application and then it's receiving data, it logs what was the error code, what was the return code, was it successful, was it not successful, and so on. The second one is basically, it allows you to log environment variables. So you could log the OS version, the Java version. So you could do something $curly brace, Java version, and then curly brace. And then basically, it will log the Java version. And then you could do that recursively. So if that Java version string contained something $curly brace, something curly brace, it will replace that and then log it. So now I can actually craft strings very creatively, and then basically the application will log data that it doesn't seem like it was logging. And then the third one is actually not related to Log4j. It's another Java feature. It's GNDI, Java Name and Directory Interface feature. So it allows you to look up information on other servers. So basically, you could do DNS lookups. You could do LDAP lookups. So you could do something which is on point A. So you could put GNDI LDAP. You put the server name. And then what Log4j will do that, it will go to the server, look up that information, and return. And then basically the last one, which is, I don't understand why. So it can return with a Java object, and then basically run it. So for example, if that LDAP server contained a Java object, Log4j will just download that Java object and will happily run it. So how would it work? And then we will see it in the demo, step by step. So let's say I'm an attacker. I actually have an LDAP server set up, and then I control it. I put a malicious Java class file on it, and then I have another machine which I run netcat listener. And then I discovered there is a vulnerable web application, and then it's running a vulnerable Log4j version. So this web application is exposed to the internet via a static IP, via a load balancer. And now let's see what I can do. So I can actually send the malicious string to the application. So let's say GNDI LDAP, and then I put the LDAP server name. So what the web application will do, it will actually, the Log4j library that the application is using, it will actually parse the string and then resolve the IB and then connect to the LDAP server. And then you can see the LDAP request, and then the LDAP server will respond, and then it will contain the exploit.class. And then what the web application will do, of course, it will just happily run that exploit.class, and then we'll execute the code what was inside the exploit.class. Like in this case, it was a reverse shell, and then we will basically see the reverse shell that was sent to the netcat listener. So that's basically how Log4j works, like in a one-on-one, not very deep, but good for like a very good explanation. So why is it so powerful? So we can see the first one, it's like really easy to exploit. Like I can just craft a string, set up a server, send that string to the application, and then it will connect to my server. And then it's due to the features that I mentioned before. And then it basically enables remote code execution, so I can run whatever I want. And then I'm not a Java developer, but I talk to my friends who are Java developers. It's basically everywhere. Like if you are using Java, like there is a high chance that you are going to use this library. And let me know if I missed anything. So what could detections and response team do? Of course, patch these systems and then identify like what should they patch. But it will take like very long time. Until this is like broadly completed, they should make sure that the Kubernetes workloads or the servers that they are running are safe, and then they should detect if they have been compromised. So for this, they would need visibility into Kubernetes workloads, services, VMs, whatever they are running, like what happened, when happened, why happened, what the attacker did later. And then they would need to do that in real time, kind of real time, and then also with a low overhead. So that's what we would like to achieve. And then this is how eBPF comes into the picture, and then basically what is eBPF, and then how could it help to us. So before diving into eBPF, I would do like a basic kernel architecture one-on-one, not very deep. I'm not a kernel engineer. You would need to ask John, who is not here today. So basically, we have three spaces. User space on the top, Linux kernel in the middle, and basically hardware on the top. I put storage and network here. There is many more, but I wanted to simplify it as much as I could. So what the Linux kernel will do as a very first step, it will abstract these hardwares away by using so-called drivers. So basically, the Linux kernel needs to be aware of hardware and enable it, but it doesn't necessarily need to expose that logic directly to the user space. So it will use so-called drivers and say like, hey, I'm aware of network devices. I'm aware of like storage devices. I'm aware of console. I'm aware of I/O. And then similarly on the user space, we have a notion of process, an agent, a user space application, and then how that user space application communicates with the kernel, it's via system calls. So for example, if you would like to do like a file I/O, you would use syswrite, sysread. You can use also send message and receive message. So these system calls are related to network connections, so this would be done when not opening a TCP socket. And then basically we have the middleware, the business logic in the middle. So this is basically like virtual file system, the process scheduler, TCP/IP, firewall technology, and so on. So what if I would like to change that logic? So what if, for example, I am an application developer, and then I would like to include in the new feature that would provide visibility and observability into my Kubernetes workloads or observe my application. So I can go to a kernel engineer and then say like, hey, can you implement this new kernel feature for me? And then he will say like, yeah, let me just code that for you. So it will take some time, months, years, but once it's implemented, it's a step ahead, but they need to convince the entire kernel community that the changes that he actually included for me, it's actually useful, it's needed, and then all the world should be paying the cost and the complexity for his feature that he is adding. But once he convinced the entire community, it's good, the changes are in. So now, as I'm an application developer, I should convince my users to upgrade to the latest Linux kernel, which is, depending on the users, take years. So, but after, I don't know, years, 5 years, they upgraded to the latest Linux kernel, and then it's fine. But the problem here is like, nobody got like 5 years, and then probably my requirements have changed since then. So how eBPF can help here? So what eBPF allows to do us, it's like pretty amazing. So if you remember like a couple of slides earlier, I talked about how user space applications communicates with the Linux kernel. So it's via system calls. And then what eBPF allows to do is actually we can take over that system call and run a BPF program on behalf of it and then return. So I put execva here, but we can take a look at other example as well. So execva is used to launch a new process. So what we can do, we can run a BPF program on the return on the execva and then extract some information. So I put bit here, binary name, and then com, but we can include much more. So we extract this type of information, and then we can export it to user space. So this is, for example, how application profiling and tracing works. But how does it actually work exactly? Like, how can we run code inside the Linux kernel? So first of all, like in the very beginning, there is bytecode. So this is actually the compiled version of the code that I showed you before. So let's say we would like to run this code in the return of every execva system call. So first of all, we use the BPF system call to load that program. And then once it's loaded, it goes to the verifier. So the verifier actually makes sure that this code is not buggy. It won't crash the Linux kernel. And then if it's buggy, and then it will crash the Linux kernel, then the verifier will reject it, and then it's not going to load. And then once it's approved, it's going to go to the JIT compiler, the just-in-time compiler. So at that time, the bytecode is really generic, so it can run on ARM, x86, whatever. And then it will take that code and then compile it to the native architecture that your CPU runs. And then once it's completed, we can attach it to the return of the execva system call. And then, so where can we hook? Where can we attach BPF programs? So I only talked about system calls, but there is like so many more. So if we take a look at starting from the top, we can actually attach to user space application by using uprobes, like user space probes. So if your application have a function, we can just like hook on that function and execute BPF code. Of course, we can attach to system calls, kernel functions, trace points, which are like more well-defined in the kernel. And then we can take it actually down to the hardware level and then, for example, offload it to the network driver. So whenever like a packet is going to be received, you can run a BPF program. And then what's really important, so it's completely unrelated to the information. So if my BPF program, it's actually modifying packets or like receiving packets, the last packet will not receive that modification before the BPF program was loaded, but once you actually load the BPF program, the next packet will actually receive it. Okay, so now we can run BPF programs, but like, what can they do? Like, how do they actually communicate with user space? So it's important that BPF programs are only the instructions. So there is no state, there is no memory allocated dynamically. And then any state is stored in BPF maps. So for example, the metrics, the statistics, the data, you actually put it into like a BPF map. And then I listed a bunch of one here, like hash tables, arrays, ring buffers, stack trace, longest prefix match, least recently used and so on. And then also like user space applications can read from that map. So for example, if you have like an agent or a CLI, it also reads from that map. And then it's also important, like these maps are completely separated from the programs. So whenever you replace the programs, the map will stay alive. Okay, so now how the development would look like with eBPF. So I'm an application developer. I can just go to like an eBPF developer and ask him like, hey, can you just like include this Linux kernel change? And then he will just do that in a couple of weeks, months, depending on the engineer, release a new version of the eBPF project, and then I can happily use it, and I don't even need to reboot my machine. So it's actually, eBPF is actually became like widely used. It's cross-platform. Recently with the Windows runtime, most Linux distros supports it, and then basically all the major cloud providers. And there are a bunch of projects which are using it under the hood for different kind of use cases. I put 3 examples here and a couple of projects, but there are so many more. So this would just give you a glimpse, like what can we do with eBPF, but there is a lot more out there. So for networking, it's mainly used for high performance and load balancing. So there is Katran, which is like a high performance load balancer from Facebook. So they switched to eBPF instead of IPVS, which is like a software-based type of load balancer, and they saw a massive performance improvement. So we have Cilium, which is like load balancing, networking, and security for like Kubernetes services. On the observability side, there are use cases like application tracing, performance troubleshooting, and monitoring. So the first 2 is BCC and BPF trace. So these are applications like figuring out what my application is doing, what my system is doing, why is it not behaving the way it should or the way I expect. We have Hubble, which is the visibility component of Cilium. So it's mostly for like network policy troubleshooting, like why my network flows are dropping, by which policy, why is it not allowed, why is it denied, and so on. And then on the security, like we will deep dive into Tetragon later, but you can use BPF for container runtime security. So basically, we have Tetragon, Tracy, and Falco here, but I just put 3 examples, but there are many out there. So you could hook like any kernel function or system call and then figure out or like detect if any suspicious behavior happened. And then you could implement also like least privilege policies. So observe all the system calls and kernel functions, network connections, file I/O that your workload should be doing, create a policy, and then basically prevent everything else. And then you could use that also for preventative security. So you could terminate on malicious activity inside the kernel. So I will talk about like eBPF-based runtime security with Tetragon that we are working on. So what is this exactly? So it's like an open source project. It's an agent that it can run on the top of any Linux operating system. So in case of Kubernetes, it's actually a daemon set, and then in case of like Linux VMs, like bare metal VMs, it's actually a container, or it can run as a systemd service as well. So it basically mounts a bunch of configuration files like policies, which will generate security observability events. So there are a lot of layers where we can extract data from. So starting from the bottom, data access and then file access. For network, we have a variety of ASM parsers, HTTP, DNS, TLS. We have visibility into kernel namespace changes, capability changes, and then privilege escalation. We have also visibility into like process execution and then system call activity. So all those events that you would observe with eBPF would go into a log file as JSON events. I will show you an example later. And that log file basically later can go to any CM system, Splunk, Elasticsearch, Sumo Logic. You can export it to S3. And then basically we have metrics like Prometheus, Grafana. These are mostly the networking use cases. So what events do we care about? So if you would observe like a malicious activity, it would do at least one of these things like network traffic, file I/O, running executables, system call activity, changing privileges, and then namespace boundaries. So this is actually how JSON event would look like. This is actually just picking up like TLS v1, which is like an old TLS version, and then we should never use it. So it contains like the Kubernetes identity information like workloads, pods, namespaces, labels. It has the process visibility information like what binary was running, like with what argument. It also includes like network connection data like source IP, destination IP, the ports, and then in some cases DNS server metadata. And then for post-processing, either you can just like ship it to a CM system like whatever you have, or you can like observe these events like via CLI, which is like more visual. That's what I'm going to do in the demo. All right, so how can we actually detect log4jshell with Tetragon? So I will just introduce the test environment, talk a little bit about it, and then I will play a video. I won't do it live, I'm sorry. So yeah. So how the test environment would look like. So as I said, Tetragon can run on any Kubernetes nodes or Kubernetes environments and as a daemon set, or in VMs as a container or a systemd managed service. In the demo, I'm just going to use a VM. I deploy it as a systemd managed service. I will apply security policies, which will actually observe network connections via TCP connect and TCP close. It will observe like file I/O, write with syswrite, and then basically file open and close with sysopen and then sysclose. And then how the log4j setup would look like. So I actually exposed this VM via an external IP. So I set this IP to static instead of ephemeral. So we can actually like reach it from the outside. And then I have a web application running on localhost 8080. I have a fake LDAP server as a container running on 1389 port. This will be important later. And then I also set up the netcat listener on the same machine on port 9001. And then I have Tetragon as not a container, but a systemd managed service. So let me just quickly try to play the video. Cool, so let's jump right into the demo. I'm going to use a testing Ubuntu VM 12.04 LTS on Google Cloud. This is the scale 2023 log4j eBPF VM that we can see on the bottom. We can see the internal IP 10.186.024, and then we can also see the external IP. And then what's really important, I set this IP to static instead of like an ephemeral IP, so we can actually reach it from the outside. And all the demo are going to be run in this VM. So let me just switch to the terminal. And then we can see basically 3 sessions here. All the sessions are actually inside the VM, so I SSH'd into the VM. So Tetragon is running as a standalone version here. So instead of like a daemon set or a container, it's actually running as a systemd managed service. So let me just quickly check the status. So all the Tetragon related information will be displayed on the bottom terminal. So if I run systemctl status, we can actually see that the service is running. We can also see that it's managed by systemd. And then if we scroll to the bottom, we can actually see that it's listening for events. So I already applied the policies which would actually observe the TCP connect, the TCP close, syswrite, sysread, and as well as the sysclose for certain files. So let me just try to observe the events first and then show you a couple of examples. So let me just try to observe the events, and then we can already see a couple of Google related ones. And then on the second terminal, I can actually run like ls-l. And then we can see that the user bin as binary was invoked. We can actually see some permission checks against the etc password file to be able to see whether the binary has permissions to actually list the directories and the files. And then we can actually see that the process exited. Alright, so let me stop observing the event. And then next, what I'm going to do, I will actually start the vulnerable web application, which actually contains a vulnerable log4j version. So it's going to run as a Docker container on the host network. So let me do that in the top terminal. Alright, so we can actually see that the container was created, and then let me try to list it. Alright, so we can see it's running. So I can actually try to open it from the browser because it's actually using the host network, which would actually use the external static IP of the Ubuntu VM. So let me quickly change to the browser again. And then since it's listening to port 8080, I can actually try to open it. Alright, so this is how our vulnerable web application looks like. So it's actually, as I said, contains the vulnerable log4j library. So in theory, if we would send a string to this application, which contains a GND lookup to a malicious LDAP server, it actually would resolve that connections while logging this string. And then basically it would connect over the internet to that malicious LDAP server, download the malicious Java class file and execute it. And then basically the malicious Java class file would do whatever we want it to do. In our case, it's just going to connect to a netcat listener, and then it's going to send over a reverse shell. So I will switch back to the terminal, set up this LDAP server, and then set up the netcat listener, and then later we will send this malicious string to this web application. So let me switch back to the terminal, and then I will make some space. Great. So let me just start the netcat listener first, and I will also start observing the events so we can actually see what's happening. So let me start the netcat listener. We can already see that Tetragon actually picked it up. And then I will also start the malicious LDAP server. It's actually using a Python script. And then, yeah, so we can see a bunch of Tetragon related events. I will go through over it later. And then let's take a moment to appreciate what we can see on the top terminal. So I took all this POC from a GitHub repository from Cosmer. It's actually great, pretty easy to use for testing and also trying out different kind of stuff. So basically this Python script set up the vulnerable LDAP server and then basically created a string for us. And then we can see that it's listening on port 1389. This is going to be important later. And then it also created the malicious Java class file, the exploit.class. And then if you take a look at the Tetragon events on the bottom, we can actually see in details what happened. So here we can see that the Python script started, and then it basically invoked a bunch of Java binary file. We can actually see that it created the exploited Java class file, and then basically we can see that the process exited. So with exit code 0, so we can actually see that it was successful. And then we can also see that it copied a bunch of other related files that we will need for this exploit. Alright, and these are the Google events that we saw before. So let me try to send this string to the web application. And then in theory, we would see that there was a connection here, and then we would actually see that we got a reverse shell on the netcat listener. So let me try to switch back to the browser and send the string. And then the password, I can say whatever we want to say. I will say welcome to scale 20x, and then let me click on login. So in theory, we should, and then actually we see that there was a connection to the LDAP server as an LDAP request, and then it actually downloaded the exploited class malicious Java class file, and then we can actually see the LDAP response with the return code 200. So we can actually see that it was successful. We can actually see the reverse shell that picked up the, or the netcat listener that picked up the reverse shell. We can see the connection was received. And then on the tetragon side, what are the related events for the malicious LDAP connection? We can actually see that there was a JREP in Java binary that connected the localhost port 1389. So this is our malicious LDAP server. And then in theory, this can be actually like an attacker controlled machine. For a testing environment, I just set up every single localhost because that was easier. We can actually see that the connection was closed, and then we can actually see another connection to port 9001, and then basically this is our netcat listener, and then here we can actually see the vmsh process that was executed. That's actually our reverse shell. So this was again against the LDAP server. This was against the netcat listener, and this is basically the reverse shell we got. So as an example, let me try to execute some commands. We can do, for example, ls-l. We can see that we are actually inside of our application container. I can try to read cat etc password. We can actually see that the binary binary was invoked. It checked against some permissions against etc password file, that it has permissions to read that files. We can actually see that the cat process with which I was actually reading the etc password. We can actually see the open and close events. We can see the exit. And then I can do the same, for example, with etc shadow. And then basically we would see the same event. So we can see that the cat process started, etc password file was open and closed, and then we can see that the cat process was actually exited. So as a last step, I will try to edit etc password, but I don't think I have Vim or any text editor installed. So let me just try to install this inside from the container. So let's just update the packages first, and then basically we can see all the tetragon related events here. So these events are actually really powerful if you export it to a CM system like Alcor, or for example to an S3 bucket, because you can create like signatures to detect attacks, or you can actually follow what the attacker was doing during exploiting this container. So let me install Vim. Then I will continue, and then I will install the packages. Alright, so now I have Vim installed. So let me try to edit its password. And then what we will see an event for the syswrite system call. And then we will see basically the file and then the content of the bytes or the number of the bytes that was written into it. Alright, so I can try to add like Natalia. And then I can actually save it. And then what we can see in the bottom that there was the Vim process invoked, and then basically there was a bunch of open and close because Vim is very noisy. And then basically here is the write event with the file and actually the number of the bytes. So you could do, for example, more malicious stuff like adding an SSH key or invoking a network connections, whatever basically we want to do. But this is just like a small proof of concept demo, like how Tetragon could have detected Log4j, and then we will include other prevention techniques and other detection techniques for upcoming CVs, because there is going to be a bunch of funds in the wrapping up section. Okay, cool. So that was the demo, and then wait. Let me just switch back to the slides. Yeah. Okay. No. Yeah. Should be. Sorry. Should be fine now. Okay. No. Yeah. I think it's fine. Yeah. Okay. Yeah. So let me just try to switch back to the slides. Cool. So the CLI actually didn't display all the information that, for example, that JSON events would take, and then, so if you would export to like a CM system, as I said, or like an S3 bucket, you could actually do more powerful stuff. You could create like signatures for detection, because as I said, it includes all the process-related information, then basically process lifecycle for pods and host processes, all ingress and egress network connections, and then basically file accesses. So you could create, like this is just a very simple example with a Splunk query. You could create signatures for shell execution. So you could actually match on like when a shell was executed inside your Kubernetes workload or a pod, which should be very malicious and should be never done. You could detect, for example, late process execution, which is also pretty interesting. So you could pick up like events that were executed 5 minutes later or like 10 minutes later your container started. So you would say like, hey, my malicious Java or like my Java application should never reach out to that LDAP server because that would be, I don't know, after 5 or 10 minutes later. You could also monitor for like leaking environment variables. So I mentioned in the beginning that Log4j allows to resolve variables like recursively. So this, for example, would actually log the user environment variable on the server side. So you could actually create a Splunk signature by matching on user bin env, which will be executed. So this is like when dumping environment variables. And then, so for prevention, I would apply the least privilege principle for network connections. So only allow the network connections that your application needs, and basically no more. So this would actually prevent the malicious LDAP reach out from the Java binary. And then for this, you could actually use, or I would actually use Cilium network policies. And then I would take advantage of like two main features, the DNS-based policies. So this would allow traffic based on a fully qualified domain name, such as api.twitter.com, in place of like IP siders, IPs, and then endpoints. And then the second one is basically deny policies. So you can define like a set of destinations that will be denied by that policy while allow anything else. And then you can also say like word, which defines like every host on the internet. So there is like a concept of word in the deny policies. So there are two pieces here. The first is basically allows connections only to api.twitter.com. So let's say I have like an application, and then I only need to connect to api.twitter.com. So the first policy will do that, and then the second will basically do like an egress lockdown, so deny everything else. So wrapping up, so a little bit of recap. So we saw like a little bit of like 101 Log4jshell in a nutshell, like why is it so powerful, and then how does it work. We saw like what is eBPF, how it comes to the picture, how it provides like full visibility into Kubernetes workloads and then VMs. We saw that it's lower at real time, and then we saw like what kind of visibility we can do, like process, network, I/O, capabilities, namespace changes. We saw an example with Tetragon, and then see how could it have caught Log4j, and then we talked a bit about like further detection and prevention techniques. So lastly, so we are working on like Cilium Tetragon, so how to contribute. Go to the GitHub repository, join the Slack channel, use the tool, report bugs, we have bugs, create feature requests, tell your user experience. We have like a bunch of layers of the stack that you can work on, like Golang, and then documentation, systems, BPF side, Linux kernel, and then packaging. And then, yeah, thank you again for coming, and then it's Q&A.
Hi, it was a great presentation. I have two questions. Number one, do the eBPF programs intercept the syscalls, or do they simply observe them? And second question is, you mentioned that there was like a lint checker or a sanity checker before they got compiled. How exactly does that work, and how does that know what is good and what is bad for the kernel?
Okay, so the first one, we actually like intercept the system calls. We can look at like f entry and then f exit. And then going deeper for the verifier, you would need to ask John. Like I know that it's checking for like instructions and then like looking for kind of bugs, but in deep details, I don't know. But I can actually like follow up with John and then make sure.
Okay, great. More questions?
Hey, there is one.
Thanks for the presentation. You had a slide earlier where you showed some other eBPF projects. There was logos but no names, and I didn't catch what they all were.
I can go back. Yeah,
Thanks.
this one.
Yeah, he was asking what the names of those projects are?
Wait, what? Which means what?
The names of the projects.
Name of the project. Okay, so it's like Catron, Cilium, BCC, BPF Trace, Hubble, Tetragon, Tracy, Falco. I can also like follow up later on the names, but if you go to like eBPF.io, and then like this is the main website for eBPF, and then you can just like find a bunch of materials there, and then there will be like a landscape, and then you will see all these applications and like 50 other more.
Okay. Do we have other questions?
One more.
Hi, I was just curious if there was any evidence of this detecting log4jshell before the CVE was announced?
Before?
Before the CVE was announced?
Yeah, I mean, so you could see all the events, like, hey, if you have like a web application, you could see, for example, the malicious like reach out. Like you could see everything, but then like you wouldn't call it like log4j. So, you know, you don't have the name. Like if the next CV would come up like whatever, like you would see all these events, it's just like the name will come like next day or like whatever. So yeah. So it's basically just like, or really just the kernel functions and then the system calls that we are basically hooking on.
One more question? Okay, well, thank you very much, Natalia, for a